So I'm going to explain how you can conduct the compiler building assignment as a part of the final report. So you just go to the assignment list and fetch this PL08 and open it. So you can hide this left pane, and you get a bunch of directories. So there are two directories not specific to any of these languages, common across all these four languages. The one is a parser, and the other is a set of test programs. And then there's one directory for each of the four languages, OCaml, Julia, Go, and Rust. And each of these looks quite similar, so has a similar structure. So by the way, you can never finish this exercise only within Jupyter. So you always need to use SSH terminal. So let me show you how the directory looks like using the SSH terminal. Just log into the server and go to the notebook folder and PL08 MinC folder, and you have this parser test, and for directories, one for each language. So first of all, there's a parser directory which contains a program that converts the C program into an equivalent expression in the XML format. So there's a MinC grammar.y, which is the definition of the grammar of the minimum C language you are going to work on. And it is converted into a working Python program, MinC grammar.py, using something called the parser generator library called Tatsu. So this is how you can actually do that. So I'm going to show you this using the Jupyter Notebook for the purpose of a quick demonstration. But you are likely to do this in ordinary SSH terminal. So you are invoking this Tatsu parser generator tool and convert it into the working Python program. So this Python program can then convert C program into an equivalent expression of ex.xml. And this is what the original C program actually looked like. So it is a very simple C program. And this is the generated XML file. So it's just a verbose XML file. But by looking at it carefully, you can understand this is a relatively straightforward conversion from the C program. For example, the XML file says, okay, so it is a function definition whose name is f, whose parameters are just one parameter, whose type is primitive type long, and name is x, just like this. And return type is long, and the body is a single compound statement here. That has, for example, variable declarations of long y that appears here, and has two statements. One is assignment statement, whose target variable is y, and the right-hand side is x plus 1. So they're faithfully converting on this C statement. So the grammar and conversion to the XML part is already provided. So basically, you don't have to look into it. But how you can develop a parser like this easily using a parser generator is an interesting subject in its own right. So also, in case you are going to extend this minimum C language for the extra work, you might be interested in modifying this grammar. So let me just briefly show you how the grammar is actually written. So go to the parser directory and just open min-c grammar.y. So this is how the grammar is written in the Tatsu parser generator. So it says the entire thing is a program followed by EOF, which is denoted by $sign. And program is the list of definitions. So what, 0 or more repetitions of definition. And then it defines definition. So definition is just a function definition. So it basically defines what you can write in the top level of the program. So in this minimum subset of C language, you can only write function definition in the top level. So in the actual program, in the actual C language, you can, for example, also write global variable definition and type definition like type def. But this syntax makes it clear that the only thing you can write in the top level is a function definition. And function definition is defined here, whose syntax is, okay, so you first have a type expression. So in the C language, typical function definition looks like this. So you start with the return type. Then you have a function name and the list of parameters and the body statement. So this is expressed in this definition. So the function definition begins with a type expression like this. Identifier, which is the function name, and open parent, the list of parameters, close parent, and a compound statement. And what is left undefined yet is parameter list, and parameter list is defined here. So this is somewhat peculiar syntax of the Tatsu parser generator. So which says the parameter list is a comma-separated list of 0 or more parameters. And parameter is a type expression followed by an identifier, just like this. And one thing that is a significant limitation of this minimum C language is that the only thing you can have as a type expression is long. So you don't have other primitive types like int, float, double. And also you cannot define new types using type def. So the only type expression you can ever write in this minimum C language is long. So like this, you just keep going, keep defining what is left undefined. So one thing that is left undefined is a compound statement. The compound statement is actually part of the statement. So statement is one of the following: empty statement, continuous statement, break statement, return statement, and you have a compound statement here. And useful control flows are if statement and while statement. And this is something called the expression statement. So you just write expression followed by a semicolon, which makes it a statement. So I hope you get the idea. You just keep going until you define everything you need to define. So all the way to expressions and various kinds of expressions. until you finally define everything, including ordinary numbers and identifier. So when you want to extend this minimum C language for your extra work, this is where you can do it. Okay, so this is the parser. And by the way, so here's one small remark about why we are using XML. Well, actually, it is not common to convert the source program first into XML and then to the whatever data structure appropriate for the programming language, called the abstract syntax tree in general. So more commonly, you simply use a parser generator for the language you write your compiler with. So OCaml has its own parser generator. So Julia has another. So it is more straightforward and much more common to read the C source code and convert it directly into the abstract syntax tree without going through XML. So the reasons why we are going through XML in this exercise are the following. So one is there's no single common parser generator usable across all the languages. Well, as a matter of fact, I had some difficulties in finding the parser generator for Go and Julia. So there may be one. But even if one exists for each language, there will be some differences between them that make it difficult, tricky, or cumbersome to explain each of them. So I resort to using parser generator for Python as a common middle ground, and let it convert C program into XML, which then can be easily read by each of these languages, whether it's Go or Julia or Camel or Rust. You have already exercised how you can use how you can read XML. So it's very straightforward to convert XML into the appropriate abstract syntax tree. And then there's one directory for each of the 4 languages you are going to develop your compiler with. So OCaml, Julia, Go, and Rust. And each of these directory has a MinC subdirectory, which then has a quite similar or the almost identical set of files that constitute a compiler. Well, specifically, there's a file called the minc dot whatever, which defines the abstract syntax tree, and minc parse dot whatever, and that converts XML into the abstract syntax tree, and minc cogen, which is essentially converting abstract syntax tree into the corresponding assembly code. And the main file that it is called from the command line. So there are slight difference between languages, but all of these directories have these 4 languages: AST, parse, cogen, and main. And everything except for cogen have already been given, essentially. So you don't have to modify any of these AST, parse, and main. So the only thing you have to modify to finish the assignment is this cogen. So in the case of OCaml, you just build it using a Dune command. So this is how you can do it. So again, I'm showing this in the Jupyter Notebook for quick demonstration, but it is likely that you want to do that in SSH terminal. So, but after you successfully build the project, you get the executable at this location. And this executable takes two parameters. One is the source XML file, and the other is the name of the file the code generator should write the assembly code into. So let me just give the XML file you just obtained before by the parser generator, the parser generated by the parser generator. So this is what happens. So you get the expression saying you have to implement this function AST to assume program. So in the MinC cogen.ml. So you can take a look at this MinC cogen.ml to see what it looks like. So this is the function that is generating this exception. So it is raising this exception. So this is where your work should begin. And of course, you are supposed to work in the SSH terminal using whichever editor you wanna use. So you just go here, MinC, and leave. So you have this MinC cogen.ml that I have just shown. So just modify this program. So complete this program so that AST2 assume program generate the appropriate assembly program for the given program, which is represented by abstract syntax tree. So exactly the same thing for each of these languages. So in the case of Julia, so you have these four directories, and so Julia has a that does not have a notion of compiling. So the all you have to do is just to make sure that minc.jl is executable. And just like before, you run this Julia program, and you get the same kind of exception saying you have to implement AST2 assume program. And this is what the MinC cogen.jl looks like. So the same for Go. So you just call Go command to build the project. And you do the same, and you get the same exception. And MinC cogen.go looks like this. So the same for Rust. You just call a cargo command to build the project. So it takes time to build dependence. And you get this executable and execute this program executable, and you get the same exception. And this is where you have to do your work in. So I'm not going into how you can actually implement this AST2 ASM ASM program, which is what the building compiler is all about. So explaining this takes entirely another video. So this video does not go into it. So assuming that you have finished or partly finished your implementation, so this is how you can conduct the test of your compiler. So there is a test directory under which you have a source directory which has a bunch of small C files. So this is the functions that your compiler should be able to compile. And there's a main.c, a file that calls one of a file that calls a function called f, which is defined one of these C files, and make file that executes all the test programs. So let me show you how they actually look. So there's a test directory, you have a source directory, and you have a bunch of C files. The simplest one is as simple as this. So it simply returns 123, and the last one is no, this one is the last. Is a function that computes the dense Fibonacci number. So each of these files defines a function called f. So the most complex one ends up defining the function called f. And then there's a main.c file that ends up calling this f function with random parameters, so for the purpose of test. So to test your compiler converts one of these C files into an assembly, and you compile this assembly, generated assembly, along with this main.c, and run it. So these tests are automated by this make file. You simply run this make command. It first converts C files into XML using minc to xml.py generated by the TatsParser generator. Then you invoke your minc compiler to compile this XML into assembly. Compile assembly with main.c to get an executable. And you also compile the original C file with main.c using ordinary GCC, and execute these two executables and compare their outputs. So all these things are automatically done by makefile. But before running the make command, you first have to set the variable minc. Maybe it was minc. I may be wrong, but you have to set this minc variable to refer to the executable you got. So it depends on which language you use to develop your compiler. And you can also set variables sources so that you can test only the subset of the 75 files in the source directory. For example, the originally it is testing all the 75 files. But in the beginning, you may want to set this into something like this, so to test only a single C file. So one thing that you might want to know is this make -n option will show you what will be executed without actually executing it. So before actually running the test, chances are that you wanna give this -n option to see what is going to happen. So let me show you the relevant part of the make file. So make file has this min_c variable. So you wanna uncomment one of these lines to reflect your language. And you might want to change this sources definition so that you only test with a certain small number of test programs, for example. So you might say, okay, so I'm working in Go and I start with only a single file. But then you run this make-n to see what is going to happen with this. So first of all, it converts f00.c into XML. Then it invokes your compiler, min_c compiler, giving XML as an input argument to get output f00.s. And then it invokes GCC to get an executable. It compiles the assembly file you obtained along with the main.c that calls a function f defined in this assembly file. And it runs the obtained executable and save the result into f00.min_c. And then it compiles the same program, but this time the original C program using a GCC to get the GCC version of the executable and execute the GCC version of the executable to get the output in f00.gcc. And finally, it compares the results obtained by the executable generated by your compiler and the executable generated by the GCC. So when you extend the min_c language for your extra work, you probably want to add your own test program. So this section describes how you can do that, but I'm going to skip this part. So when you do an extra work, read this section and then appropriate test programs. So at the end of the day, what you should do before submitting your work is to make sure you pass all the tests for which you are supposed to do this. So of course, when you do this right away, the test immediately fails because the compiler simply signals an exception I have just shown. So after some effort, you might end up having some tests still failing. So in which case, you might want to give -k option to the make so that it runs all the test cases. And so normally without this option, the make immediately stops when one of these tests fails. But if you give -k, it keeps going. So you can run all the tests you succeed. So after you have done all the tests, write your results into this Excel sheet I have already shared with you. So it looks like this. So there's a row for each of these tests, and you write either passed it passed the test, C which indicates it cannot assemble. So your compiler fails to produce an assembly program. So the compiler fails in the middle. So I indicates your compiler generates some assembly code, but the assembly does not compile with GCC. So it generates essentially an invalid assembly code. So R indicates your compiler produces an executable. So your generated assembly does compile with a GCC, but the resulting executable does not terminate successfully. Oh, what is that? Okay, so and the finally, so W is the wrong result. The executable runs successfully. It doesn't end with an error, but the output is not identical with the output from the GCC generated executable. So classify the results into one of these 5 categories and put the results into this table. And as always, so please write a summary of what you have learned and some reflections on the subject and assignment. And if you do something extra other than the minimum requirement of passing of these tests, so please write a summary of what you have done in addition to the minimum requirement. So there are some suggestions about the extra work you want to do, like some syntactic extensions, introducing for loop, for example, which is relatively straightforward. Given that you have already you are already able to compile the while loop. So going into for loop is relatively straightforward. So there are some other suggestions you might want to work on, but you can of course work on something else, and whatever you have done extra should be written into this extra docx. So I think that's all I need to say. Good luck.